Let me just thank the organizers, first of all, for their kind invitation to join you at this exciting conference. I'm actually new to this community, and so today's talk will be a little bit different than what you've heard, at least in the session. But certainly, I think some of the aspects of what I'll be talking about would be of interest to some of you. The focus of my talk is going to look at singly charged, low-energy heavy ions that are interacting with surfaces in particular. So this is an ion-surface interaction talk. But in particular, I'll be focusing more on the ability for us to look at the complexity of energetic ions as they interact with the surface, our ability to look at how the energetics of those interactions can influence and drive these surfaces very far from equilibrium, inducing some very interesting nanoscale phases. I'd like to just acknowledge here Brendan Holby, who is my PhD student, and Akshay Shetty, who is my postdoc in this work. So a brief outline then of the talk. I will give you an overall description of the Institute tools that we use in my laboratory. One in particular focuses on using Institute XPS, but there are some other techniques that I'll talk about, and also some of the GSAX data that we have. And I will use two case studies as examples of some of these very interesting interactions. So there will be some practical aspects of the talk, but it will be motivated by some fundamental questions that we're still tackling with. We'll be focusing on nanopatterning of semiconductors, in this case, the silicon and 3-4 semiconductors. So let me just start off with this slide that summarizes the overall complexity of what happens to an incident energetic ion when it interacts with the surface atoms. And to give you a sense in terms of the scales that we're talking about here, a 500 electron volt argon ion that interacts, for example, with silicon will only penetrate about 10 nanometers of the surface, just to give you some scale. That interaction is not just relevant in terms of the spatial scale, but as we nicely heard this morning, there's obviously the spatial-temporal gap that we have in terms of being able to probe a lot of mechanisms that are driven at both time and space. Our challenge is, in fact, that we're not dealing with photons and electrons per se. We're here dealing with the interaction of ions that if you were to, in fact, try to probe some of the complexity that you see here in the coupling of the ion and the material, as is illustrated here, of course the challenge would be not the probing aspect of it necessarily, but certainly the pumping part of it. The point here is that in the time scale of interactions of, let's say, the singly charged ion that interacts with the surface, the emission, or let's say the physical desorption of that atom at the surface induced by the energy of the incoming ion, known as sputtering, is only one of many mechanisms that occur in timescales that differ drastically that lead to changes on the surface. So what this is saying basically is that not only are we dealing with physical sputtering here, but we are dealing with defect dynamics that evolve over time and space that can generate, what you see here on the left, a complexity of rich morphology on a surface. And on the same surface, with a low energy ion, you can induce a variety of different phases, from well-organized quantum dots all the way to mesoscale structures and even complex nanotrendril structures like you see here, even below, for example, the damage threshold of some of these materials, which is very interesting from a fundamental point of view. Here's another illustration that hopefully also sends the message home. We're dealing with nanoscale interactions of low-energy singly charged ions that interact with the surface. In the case, for example, of a plasma, you have additional interactions that in the atomic physics, as you well know, right near the surface that induce changes at the surface of the material, again, inducing changes over time. And in particular for us, our interest is not just seeing these changes in the prompt time scales, but more importantly, as these changes occur and cumulative changes on the surface occur on time scales of minutes to even hours, we'd like to see how this evolution evolves. So one of the aspects that we like, that we're interested in when we look at ion surface interactions is to look at it from two different perspectives. One has to do with the balance between the stimulus rate, which is in this case would be the plasma source or the energetic ions that we use, against the material response rate. And depending on how well you can manipulate and direct the balance between the two, you are able to reach different metastable phases, metastable states. You can, for example, disorder the material. You can get into defected self-organization, or in fact nearly perfect self-organized systems, where the atoms self-organize, the energy that's delivered to the surface is not only sufficient, but directed in a specific channel where the atoms can arrange themselves in a specific way. One of the challenges, though, to be able to manipulate and direct the pathways for this type of synthesis has a lot to do with how we manipulate the particles that arrive at the surface. So, for example, when we look at our tool set, and when we look at how we like to approach this question of how we can manipulate particles at a surface to induce some kind of pattern, for example, we like to have a well-established source of ions, in this case, where we, for example, can change at will the energy, the incident particle energy, or the angle with respect to the surface. Or we like to be able to reach certain fluxes and fluences. We like to be able to probe at the same time, in fact, that we're doing the modification, probe the surface and subsurface. Not only the surface atoms that are interacting with vacuum, with that interface, but also the subsurface, since of course there are energetics involved that are driving some diffusion from the subsurface back to the surface that can influence, in fact, the patterns that you form. And finally, also the emitted species that are coming off the surface that carry information about some of the fundamental mechanisms that drive the pattern. For us, and for this talk in particular, I'd like to point out that we look at two very specific spatial scales. We look at the first monolayer of the surface, as that is in fact what we define in our field as the sputter depth, or the depth from which you have ion-induced desorption of these atoms back onto the vacuum, and the subsurface layer that can range anywhere from a nanometer down to, in fact, even deeper, about 8 nanometers. And we do this, we probe these two spatial scales separately by two different techniques that I'll discuss briefly in this talk. The other point I'd like to point out is that all of this is in situ, and these measurements that we're doing as, in fact, the bombardment is occurring and the ions are interacting with the surface, the time remains static. So, I'd like to point that out. We had a beautiful talk this morning about this point, and in fact, what you're going to be seeing is, I would call it dynamics, but in the sense of time scales, note that for us to look at the modification and, in fact, the fluence levels that we deal with to induce these metastable phases, we're talking about order of seconds to minutes to hours that we like to probe. So this is the facility that we use. It's called Ignis. It's a facility that has the capability of applying energetic ions to surfaces. This could be also under high pressure. So the system, in fact, is the analyzer and the spectroscopy can be carried up to very high pressures. And we're, of course, focusing on these interactions on the surfaces. And in particular, we use a number of different tools. Part of being able to decipher how these mechanisms evolve under radiation of ions necessitates our ability to be able to have complementary techniques watching the surface at the same time. So what I mean by that, for example, is low energy ion scattering spectroscopy can probe the first monolayer, and we try to use techniques that in fact complement that spatial resolution. So for example, We also take advantage of using UV photons in some cases, also look at recoils, for example, to look at the surface. And as we go down to the subsurface and across from the surface down to 8 nanometers, we get into techniques that we have such as X-ray photoelectron spectroscopy and even angle results, so we can get the information of how the composition changes over time as we radiate. In addition to this, of course, we like to correlate what we see in the chemistry, and you'll see this in the motivation shortly. What we see in the chemistry, we like to correlate that to what we see with the morphology, that is, how the atoms are actually arranging themselves. In this case, we're using a rather high-resolution SEM to look at some of the structures, given the size of the structures that we're looking at. Now, added to these measurements, we also have to get a sense of the morphology from a complementary technique, and in fact we use GSACs, which is glancing incidence scattering of X-rays that in fact are in a station coupled to a broad beam ion source, so this is an in situ technique, and we also take these measurements to correlate back to the measurements on the facility that I just presented. All right, so let me just give you a sort of general background as to what are some of the aspects about surfaces that we're interested in, and why are we paying attention right now at low energy heavy ions to do some of the interesting patterns that occur on these materials. So first of all, energetic ions, when you expose a material to them, are not only going to generate defects and damage, but in fact you can tune their energy and their energy and incident angle, for example, and other parameters to induce patterning at a surface. And in fact, if you look at just fundamentally what this is in terms of the interaction of the ion, it's a competition between the erosion or the sputtering, let's say, of the atoms away from the surface, and in fact the relaxation mechanisms that drive atoms diffusing along the surface. Very much, for example, as you see here in this nice comparison in this paper, where you see the ripples on sand dunes in Morocco and the kind of structure that you can get by irradiating silicon with argon, very similar physical mechanisms can take place, inducing these kinds of patterns that we see in nature. Okay? One of the key differences, though, and one of the aspects of this that are still key questions related to our ability to control these patterns, have a lot to do with an understanding of both the prompt effects, which deal with the ion-induced defect dynamics near the surface, and the relaxation effects, or long-term effects, which is thermal diffusion of atoms as they, in fact, relax over time on the surface. And tied to this, there is a very important point which is related to the compositional that appear to be, in fact, very important in driving some of the patterns on the surfaces. So one of the important studies lately that has heightened the importance of surface composition has been the studies by several groups, in fact, looking at patterning of silicon quantum dots on surfaces. If you radiate a silicon surface with argon ions, so these are heavy ions, singly charged, at energies of around 500 eV or 1000 electron volts, you will in fact get a flat surface. You will smoothen the surface. You will not have an instability to in fact drive a pattern on that surface. And as it turned out in this particular field, there were a number of studies that in fact found that metal impurities that were inadvertently included in some of the experiments that were done, in fact induced pattern formation. And I say inadvertent because it was actually not known that this was done until there was a number of different studies that elucidated this. And the part of this that was very important was the fact that there was some fundamental mechanisms involved with the interaction of the ions, the silicon atoms, but in particular, the metallic composition of the surface. So this, in fact, motivated some additional studies in our group to look at, specifically looking at low-energy singly charged heavy ions, in this case argon, and look at silicon, but silicon deposited in a very thin layer of a metal, to address this conjecture about the role that concentration and composition on the surface plays in terms of developing these patterns at the surface. So that will be the first case study that I'll be talking about. And the second is not looking at silicon, but looking now at a more complex system, in this case a compound semiconductor. We've looked at a number of them. We're going to look at the gallium antimonide system primarily, and how in fact these similar low energy ions in fact can induce changes in patterns on the surface as well. So here's silicon, and again I mentioned this study where in fact this is a nice work done by Carl Ludwig's group over at Boston University, where they did a number of studies to look and in fact elucidate that when you bombard silicon normally with argon ions, you can induce these very nice patterns on the surface only when you have in fact metal seeding. When you don't have any metal seeding, in fact, so this experiment was nicely controlled by having a very thin silicon layer here. There's no inadvertent metal seeding here. You get a flat surface. So the role of surface composition, certainly during the time of modification, became very important, and in fact still a critical knowledge gap in the field to understand how this actually happens. So we set up an experiment to study this. As I mentioned, we deposited about 10 to 20 nanometers of a variety of metals. So we conjectured that in fact what drives some of these patterns are probably related with the strong silicide formation that could possibly form near the surface that could drive some of these patterns that you see on the surface of silicon. And so what we did is varied for different types of films, different metal silicide formation, if you will, with the samples. And what we did is in situ measured with XPS. We had a sample that was in fact covered with one of these metal thin films. In this case, for example, you see on the left-hand side is gold. This is a cross-sectional XPS spectra. So you see the peaks here for gold. You see the peaks here just for silicon. So this is the thin film covered side of the sample. And the same sample is exposed to irradiation under these conditions. And you notice that it's only the side that in fact had, the side that actually had the gold covering, the gold thin film, where you get these dots. Now what's important is that the side that actually had the gold, the dots that you see here are not gold. In fact, it's silicon. And so when you look at the gold-coated surface, and we take that surface and look at it closely with TM, you find that in fact these are silicon quantum dots that you can actually create by working with the ability for you to manipulate the concentration of metal on the surface of silicon. But again, the question is why is it and how does this happen? What fundamentally happens at the surface that leads to this, this instability and eventually this patterning? And so we closely studied the concentration of both the gold-covered and non-gold covered samples. So this is the gold-covered sample with ion scattering spectroscopy, which again, remind you, is sensitive to the first monolayer, and XPS. And we find that in fact, if we go back and correlate the formation of the structures of the nanopattern, we find that there is a very strong link, not only with the fact that there's a presence of a metal there, in this case we use gold in this particular example, but in fact is the concentration. It's only about 1 to about 3 atomic percent of that metal that induces that instability. Any additional, any higher amount of metal, in fact, it just leads to ion-induced mixing at the surface. It is that 1 to 3 atomic percent metal composition that in fact turns the instability around so that you can induce the pattern. We found this, for example, with all types of different films that were used on silicon. So we were trying to tune the heat of formation for the silicides. So for example, for those silicides that were easy to form, we were able to form nanostructures at a smaller, lower amount of percentage, if you will, relative percentage of iron, let's say, or metal silicide compared to another. And if you see here, these are GSAC's data. What this is basically the autocorrelation function that in reciprocal space, what it's just telling us is these peaks are correlated with the formation of structure on the surface. Okay? As you see here with time, you see that there is a very specific fluence in which these nanostructures actually grow. And in fact, these, again, have been correlated back 2 to 4%. What is this? Battery issues here. Okay. So that's silicon nanopatterning. What happens now when you have a combination, in this case, on a compound semiconductor? So compound semiconductors also radiated can lead to pattern. And here, for example, is data on irradiation of gallium antimonide. And the conjecture in this particular case is that here the composition also at the surface is important. What drives the patterns here is an agglomeration of gallium that becomes a shield, if you will, for erosion that leads to the growth of the structures. And so we started working, for example, with neon singly charged ions on gallium antimonide. This is data at 500 eV, and you can see that these very beautiful patterns can be induced. And the question is, how is this being driven? And so we looked at GSAC's data that looked very closely at the fluence levels when these patterns in fact evolve on the surface. And in fact, we started looking at very detailed surface-sensitive data that looked right before we induced the patterns. We looked at the way the composition changes. And we found that something very interesting, that in this particular case, for krypton, we see this enrichment right before the patterns of antimonide and a subsurface enrichment of gallium. And it's in fact that subsurface enrichment of gallium over time that is in fact inducing the overall patterning laterally on the surface. If we look, for example, at the GSAC's data, we find that there's really nice correlation when the patterns begin to start to, in fact, that increase in antimony at the first monolayer and very large increase of gallium that accumulates at the subsurface layer that is, in fact, driving the pattern. Well, you can actually generate these patterns not just at order of 500 electron volts, but even an order of magnitude lower. Although this may be high energies for some of you in your work, these are quite low energies in our work. In fact, this is what we call the sub-threshold damage energies for gallium antimonide. And in fact, the sputtering, in fact, the threshold for sputtering, or the ion-induced absorption for these materials, are of the order of about 50 to 60 electron volts. So how is it that we can actually manage to create patterns at energies below this? And what's very interesting here is that there's quite a different mechanism at the very low energies like this that is driving the pattern. And we're finding that in fact, the size of that pattern can be scaled nicely with energy. And when we get to these sub-threshold energies, the erosion is not the dominant mechanism anymore. It becomes the mass redistribution on the surface, or the ion-enhanced surface diffusivity that becomes relevant in this case. And the last example I'd like to give here is one that is very peculiar, related to not gallium antimonide, but gallium arsenide. If you take gallium arsenide and bombard it with the same singly charged argon ion at the same energy, you don't get any pattern like you did in gallium antimonide. In fact, you have to go to relatively heavier incident ions. In this case, we're doing this with xenon on gallium arsenide. There you, in fact, are able to induce this instability and create patterns on the surface. Question is, why? And so as we closely look at the coupling of the ions on the surface, we go to computational simulations to couple the in situ results in the experiments to, in fact, understand the multi-component nanopattern. So here on the left, what you're seeing is experiments that are bringing an ion beam, in this case a silicon, in gracing incidence to the surface, creating this ripple-like structure. What you see here in the right is, in fact, the modeling that's predicting that response. And if we now evolve and develop the models to expand them to two-component systems, like the system in gallium arsenide and gallium antimonide, we're able to then look at some of the physics that are going on and why the differences between xenon and krypton appear. Well, it has to do with the energy deposition at the surface. And so this is the case for xenon in incident on the surface of these compound semiconductors. And we found that, in fact, it was the melt volume generated by the local energy deposition at the surface that tended to, in fact, dominate the patterning on, for example, in this case, gallium antimonide when compared to gallium arsenide. So this is, in fact, these are examples for argon on these different semiconductors, and you can see that argon, krypton, and we have the case for xenon has, in fact, you can see the difference between the melt volume and, in fact, correlate that back to the pattern. There's still some questions, of course, that we have about the way the patterns evolve related to the prompt effects. It's not enough to conjecture just the melt volume that, in fact, is responsible for some of the differences seen here. The point here being that, for example, we see a difference in melt volume between the gallium antimonide, gallium arsenide for xenon as well as for krypton and argon. We do question whether also there's an ion-enhanced diffusivity, which in fact we cannot measure directly, as that is a prompt effect of the order of picoseconds to nanoseconds. So in fact, we're also conjecturing how, in fact, the ion-enhanced diffusion can be, in fact, contributing to the lateral patterning that occurs in these surfaces and helping to explain why, in this particular case, in gallium antimonide, you can pattern with argon while in gallium arsenide you cannot. There's also, a lot of this work is also leading us to look at more complex materials. So, for example, we're looking at bulk metallic glass surfaces. The combination of particles that are incident on these type of glass surfaces become very relevant. So we're combining these low energy ions, but adding photons, in fact, to induce changes on these metallic glass surfaces that not only allows us to change the morphology, but also is allowing us to change the chemistry. So there's a lot we're learning about how these ions are inducing patterns and how additional type of particle beams, in fact, can induce changes on these materials. Let me just now summarize. So in situ surface characterization during the particle irradiation can shed some light about how these nanopatterns occur. Of course, our limitation here is limited to, in fact, the timescales that we probe with respect to the prompt mechanisms. With respect to the time, in fact, that the modification occurs, which are these long temporal times, this, in fact, is not the case. So there is a very important need to complement this with computational simulations, and in fact, some of these prompt effects are now being studied by computational tools in our group. And we find that in these semiconductors, in fact, the driving mechanisms are related to compositional changes, understanding the fundamental binding mechanism, and also enhanced surface diffusion is in fact part of the story of inducing these patterns. And with that, I'd like to thank you for your attention and open for questions.